watching it twice, we should have answered all the questions, I hope. We have to watch it 10 times by the end of today, so watching it twice I think is okay for you guys. All right, let's start by going over it. Hopefully it gave you kind of a better idea of just how small atoms are, okay? Trying to compare them to real life things that you understand and know. So number 1, so the number of atoms in a grapefruit would be equivalent to what? Let's get our participation in for the week. Olivia.
The size of the Earth.
What would be the size of the Earth?
The number of atoms.
Number of atoms, okay, awesome. Yep, they compared the atoms to what? Finn? Blueberries. Number of blueberries to fill the Earth would be the amount of atoms in a grapefruit, which is a wild comparison in my opinion. So number 2, if you had an atom that was blown up to the size of a blueberry, how big would the nucleus be? Grace?
Invisible because it's so small.
Yeah, absolutely. It would just not be visible at all. So we take it a step further. He blows up the blueberry to the size of a house. Was it visible then?
Barely.
Barely visible? Yeah. Gotcha. And I'll move on to the... he blows it up to the size of a football field, but I'll go back to that. But number 3, this is review. What is contained in the nucleus of an atom? Megan?
Protons, neutrons, and electrons.
Not in the nucleus. Electrons aren't in the nucleus, just the protons and the neutrons. Yep. Good job. All right, number 4. Most of the atom is considered to be what? Noah?
Empty.
Empty. Empty space, which is also crazy, right? All right. 5. The density of a typical nucleus would be equal to what? Lucas?
4 times 10 to the 17th power kilograms per meter cubed.
True. Yep. That was his first numbers and units he gave you. But it's kind of hard because we're in America and we don't really use those. So what else do we got? Jacob?
2.5 times 10 to the 16th power pounds per feet cubed.
Yep, that's a little bit more understandable for us here. What was the last thing he compared it to with the density, Lucas?
6.2 billion cars fit in one cubic foot box.
I don't know how to show this without. Picture a foot by foot by foot box, so like this big, putting 6.2 billion cars in a box this big would equal the density of your nucleus of a normal atom, which is wild. So very dense. Good job. And number 6, kind of reverting back, so the blueberry was blown up to be the size of an atom, then the size of a house, and then the size of a football field. So we're describing the size and scale of an atom, explain the relative size of the nucleus in relation to the size of the entire atom. So when they talked about the football field, what did they say the size of the nucleus was? Megan?
The size of a marble.
Size of a marble. So picture standing in a football field and a marble was put in the middle. That's the size of your nucleus on that scale, which is pretty crazy as well. Nice. I'd hold on to this because there's definitely some good test question material, quiz material on there. All right, so we're moving back onto the notes, okay? So we're going to talk about some very important vocab terms. There's 3 of them. They're they have the same like words in them, but they do not mean the same thing. And there are some similarities and there are some differences. So we'll need to pay attention to those. So the first one we're going to talk about is our atomic number, sometimes referred to as Z. Don't worry about that for now, but I just put it up there for reference. This is our number of protons in the nucleus. We know this, and there's a great way to identify it. Here's the element carbon from the periodic table. We have our atomic number here, right? Atomic number for carbon is 6. Based on what the atomic number is, we know that carbon has 6 protons. And that's that. That is the easy way to figure that out. It helps to identify the element. When you change your protons, your element's going to change. Okay. For the time being, just a note, our electrons are going to be the same as our protons for first semester. In second semester, that's going to change. But if you have 6 protons, you know you're going to have 6 electrons for the time being. Every time. All right. Now we have our mass number, also could be identified as A. Okay. This is our total number of protons and neutrons in the nucleus. So a good way to think about this is our number of neutrons plus our atomic number. So P plus N. You want to think of it like that. Losing my train of thought here. I think that's all I got. Oh, okay. So whenever you see mass number or atomic number, know that that's going to be a whole number, okay, if that helps you to identify it. So atomic number is always not going to have a decimal in it. Mass number is not going to have a decimal in it. We'll talk about that in a moment. It's usually going to be given to you, okay, our mass number, or we're going to ask you to round the atomic mass, which is what I'm going to talk about right now. Okay, last one is our atomic mass. This is the one that's going to have a decimal in it. Atomic mass is defined as the average mass of all of our naturally occurring isotopes of a certain element. You're probably wondering what an isotope is. Not sure if that's necessarily review for you. We're going to get into the isotopes specifically on Monday. An isotope is an atom with the same number of protons, but a different number of neutrons. Remember I just said that protons, that number, if you change it, will change the element. Okay? When we're referring to an isotope, we are changing the number of neutrons, which is changing the mass slightly. It's easy to think about it as same element, different masses because of the change in neutrons. We're also going to talk about this more in nuclear chemistry down the line. All right, we good? Can I move on? All right, so take a look at your sheet here. We're gonna go through some examples to kind of identify our protons, our neutrons, electrons, as well as our atomic number, mass number, and our atomic mass. So the example I've pulled up for you is fluorine. I've just taken a snapshot of a periodic table version of fluorine. And I know right off the bat that I can identify my number of protons by my atomic number. And the atomic number for fluorine is 9. Atomic number might be placed in weird spots sometimes. It could be here, it could be on the other side, it could be in the middle. But remember, you're looking for that whole number. Normally it's at the top, a lot of the time. So we know if our atomic number is 9, we have 9 protons. And because I stated that for semester 1, our electrons are going to be equal to our protons, we know we also have 9 electrons. Okay. Now we're going to have to determine our number of neutrons, which takes one very simple math thing. So we know our atomic number is 9. Determine those things. We know that our atomic mass, that's this number with the decimal, and it's also right here. This is the decimal value that you'll see on the periodic table, is 18.998. So our mass number is 19 because we rounded that up, okay? Sometimes we might give you a number. Sometimes we might say, hey, you need to round your atomic mass up or down to the nearest whole number. So if we have our mass number and we have our number of protons, all we're going to do is take our mass number and subtract our number of protons, which gives us our neutrons, which is probably a breath of fresh air to you after doing dimensional analysis. Now all you have to do is subtract or add. Does this make sense? Thought so. We'll do one more example, and then I'll have you guys do one. All right, looking at chlorine. Chlorine has an atomic number of 17. So how many protons do we have? 17. Okay. So how many electrons do we have because protons are equal to electrons? 17. Okay. Atomic number we already acknowledged as 17. Okay. Our atomic mass is 35.453. So in this case, our mass number rounded is going to be 35. How do I get my neutrons? Ashley.
Mass number minus the atomic number.
Yeah. 35 minus 17, which gives us 18 neutrons. Simple as that. All right, this one wasn't on your sheet, I don't think. All right, take a minute. You guys have oxygen that should be right next to fluorine. I'm sure a lot of you probably did it as I was talking, which is fine. I'll just give you guys a second and then we'll go over it. A lot of you look very bored today. Is it because it's Thursday? Yeah, it's dragging on. Understand it? We all good? All right, you guys tell me. How many protons do we have for oxygen? You can just shout it out. It's fine. 8. How do you know?
In the course or the middle this time.
There was some mumbling there. What? Atomic number. Okay, so our atomic number is also 8. And on this version of the one that I pulled, our atomic number is weirdly in the middle. Awesome. So how many electrons do we have? 8. Why?
Because you said
Same as protons, yes. For semester 1, yes. All right, so we now need to calculate our neutrons. We know that our atomic mass is 15.999. What do we think that our mass number is?
16.
Why? Round it up, so we have 16. So what do we need to do to get our neutrons?
16 minus 8.
You guys are so thrilled about that.
Yeah.
Which is 8. Wow. Crazy, right? All right, so in this instance, unlike the other two examples, our protons, neutrons, and electrons are all equal to each other. That will occasionally happen. So, great. Fantastic. This is the easy stuff, okay? All right. Onward. We're going to talk a little bit about different ways that we can view atomic structure and kind of how it's been developed over time. So you don't have this image on your sheet because I had to modify it a little bit, so just stare at it and listen. So there's been a lot of scientists over time that have been involved in developing what we know as the atomic structure and understanding what makes up an atom. I know a lot about the scientific portion. Mrs. Simpson knows a lot of backstory on all these scientists, which is pretty cool. She'll talk a little more about that tomorrow. I'll give a little bit of brief information for what I have for now, but something I want you to notice here is that 1803 is when our first guy really... Mrs. Simpson has some opinions about John Dalton, so I'll let her talk about that tomorrow, but this is when somebody really started thinking about, okay, what are we made up of? Okay, how small is it? What properties do we have? Okay, for each of these different elements. And then after that, we have a couple other people, and you can see that the gap between the years is a lot smaller because they have affected each other in those developments. They've worked off of each other's models that they developed to become more advanced and correct. So with that, we're going to talk about J.J. Thomson's plum pudding model of the atom. Please raise your hand if you know what plum pudding is. Exactly. Nobody today has known what plum pudding is yet. It's a sad Christmas dessert, apparently, of like a dense cake with raisins in it, which is like an English dessert that he based his model off of, which will make sense when I come over here and show you. So the equal to sign. He viewed the atom as a positively charged something, some sort of matter, with electrons that are negatively charged just kind of spewed about in there, okay? And how that relates back to our plum pudding model is if you look at this gross thing, you see that there is like a cake, but then inside we have whatever the plum raisin things are that are kind of scattered throughout, okay? That's how he viewed and thought the atom was made up of. Now, nobody knows what plum pudding is now. So another way to refer to it is the blizzard model. So if you think about a DQ blizzard, right, you go and you have a base of ice cream, right, and then you add your toppings to it, and the toppings get mixed in, and it's very similar to the plum pudding, okay, it's just randomly mixed throughout, which is the viewpoint of this model of atomic structure. Now, we find out later on that this is not correct. Okay, it's a good idea, but it's not right. Okay, then comes along Ernest Rutherford, and he develops the nuclear model. Now, in this unit, in this instance, when we say nuclear, we're not talking about bombs. Okay, we're talking about nuclear is equal to the nucleus. We do have a nuclear unit, which we will be talking about, the atomic bomb and all that jazz, but not right now. Okay, so this scientist discovered, I should say, that there is a central nucleus in the atom. So the plum pudding model didn't really have a nucleus. There was some sort of positively charged matter. He didn't know what it was, okay? Rutherford figured out that we do have a nucleus that's composed of our protons and our neutrons. And he also developed an understanding that we had electrons that weren't necessarily inside the nucleus itself, but in some way around it. He didn't really understand it yet, but when we look at this over here, we can see that he has the positively charged nucleus, and then we have our ovals or elliptical shapes that are showing electrons moving. But he didn't really have an understanding of that yet. We will talk about more in detail his gold foil experiment, which is really interesting, that helped him come to this conclusion a little bit later on. Tomorrow? Are we talking about it tomorrow? Maybe tomorrow. So we'll get into that. All right, and one of the last ones that we're going to talk about today is our Niels Bohr model, or just the Bohr model. Now, this is where we start to see a little bit more development with our atomic structure. So if you look at it here, we see that we have more of a detailed, you can count them, protons and neutrons in our nucleus, but then we can see that we have sort of like this ring structure around it, which is symbolizing our orbiting electrons. Okay. Bohr started to understand that these electrons were in energy levels. He didn't necessarily understand everything with that. So there was a limit to what you could understand. It was movement, right? I keep forgetting every single hour. The movement of them. He understood the energy levels, but he didn't necessarily understand the movement from how Simpson describes it, staircase, the different levels, which we'll get more into detail. That probably doesn't make much sense to you right now. Why we use this model is because it's a great visual. It's really good to look at and say, okay, I can see what my element looks like. I can see my protons and neutrons. I can see all the energy levels. I can see how many electrons it has, possibly later on, how many electrons it might need, things along those lines. Something kind of cool about this model is if you Google really any element, I think, I know that I've done a good chunk of them. If you Google it, it'll give you obviously like what it is and all its information, but in the bottom corner, there's actually like a 3D model of the Bohr model that you can like flip around and like see. It's actually pretty cool. I played around with it a little bit before putting together this lesson because I thought it was kind of cool. Finished kind of early. All right. I think that covers pretty much everything for structure today. Tomorrow, we're going to do some group activities on mass number, atomic mass and atomic number. Mrs. Simpson is going to go over some cool facts about those scientists that we briefly talked about, and we'll move forward from there. I finished early again.